Okay, let's get right into it. Welcome to your complete, totally boredom-free explainer of Chapter 11, Electricity. If you're in the 10th standard, you probably already know this chapter can feel kind of like a massive tangled web of formulas, confusing diagrams, and some really tricky numericals. But hey, don't sweat it. Today, we're going to untangle the whole shebang. We're breaking down these concepts into a top-tier cheat sheet, giving you the exact shortcuts, memory tricks, and real-life analogies you need to not just pass, but absolutely crush your exams. So get comfortable, focus up, and let's decode electricity together. To kick things off, let's start with a massive, curiosity-driven question. I want you to think about the wires around your room right now. What is actually happening inside them? Like, what invisible magic makes electricity flow through a solid piece of metal just to turn on your lights or charge your phone? Hold that thought, because we're about to shrink way down and take a journey right alongside a charge.
So, let's jump into Section 1, Meet Electric Current. Before we get bogged down in complicated math, we need to understand what we're actually measuring. Imagine a river. When we say water current, we're literally just talking about the flow of water molecules moving down a stream, right? Well, an electric current is the exact same idea, just with different ingredients. Instead of a river, we have a conductor, like a copper wire. And instead of water molecules, we've got negative charges, specifically tiny little things called electrons flowing through it. That is it. Electric current is just the flow of negative charges. Keep this water analogy in your head, because it's going to save you multiple times today.
Now notice how we turned that simple idea into an exam-ready formula. If current is just flowing charges, how do we measure it? We measure the rate of that flow. You know, in science, whenever you see the word rate, it's a massive clue that you just need to divide by time. So, electric current, which we represent with a capital letter I, is simply the amount of charge, Q, divided by the time it takes to flow, T. So I equals Q over T. Charge is measured in coulombs, time in seconds, and current is measured in amperes.
The absolutely crucial point here is understanding just how much charge we are actually talking about. 6.25 times 10 to the power of 18. Guys, that is 18 zeros. I want you to lock this number into your brain because it is an ultimate exam cheat code. Examiners love to ask, how many electrons make up just one single coulomb of charge? And this right here is your answer. It takes billions upon billions of these tiny flowing electrons to make up just one single unit of charge.
Moving right along to Section 2, the push, also known as potential difference.
Okay, so we know that current is the flow of electrons, but here's the interesting part. Why does it flow at all? A random, unconnected piece of wire just sitting on your desk doesn't shock you. The electrons are in there, sure, but they aren't moving in a straight line. So what's the invisible force actually driving them through a circuit? Let's bring back our brilliant water analogy to visualize this. Water in a perfectly flat pipe just sits there. It only flows when there's a difference in gravity, when one end is higher than the other. Water flows from high to low. Well, in a circuit, charges need the exact same thing, a difference. But instead of gravity, they need a potential difference. And what creates this electrical high and low ground? A battery, or a cell. The chemical energy inside a battery creates the pressure, that potential difference that literally pushes the electrons through the wire. No potential difference, no flow. It's that simple.
Now, let's figure out how we define this for your exams. Potential difference, represented by V, is the work done to move a charge. The formula is V equals W over Q, work divided by charge. This is a direct board exam favorite right here. If they ask you to define 1 volt, you just plug a 1 into everything. 1 volt is when 1 joule of work is done to move 1 coulomb of charge from one point to another. Just visualize physically carrying a heavy box of charge across a room. That takes work.
Before we move on, I gotta drop a massive exam hack for you. You will definitely be asked to compare the two essential instruments of this chapter. The ammeter measures current, and it is always connected in series, meaning right in the main line of the circuit. The voltmeter, on the other hand, measures potential difference, and it is always connected in parallel, meaning it branches off across the 2 points you're actually measuring. Memorize this comparison. It is the easiest marks you'll ever get.
All right, Section 3, the golden rule, Ohm's law.
Grab your mental highlighters, because this is arguably the most important part of the entire explainer. The German physicist Georg Simon Ohm figured out a beautiful relationship. He stated, the potential difference is directly proportional to the current, meaning if you increase the battery power, the push, the current, the flow increases too. Makes total sense, right?
But wait, look at that second half of the quote. Provided its temperature remains the same. I am aggressively highlighting this for you right now. Do not forget the temperature condition. Examiners will set a trap by asking for Ohm's law, and if you leave out the temperature part, you lose points. So, mathematically, how do we show this relationship? With the legendary formula, V equals IR. Voltage equals current multiplied by resistance. When Ohm made his proportional relationship into a hard equation, he had to add a constant. That constant is R, resistance. And resistance is exactly what it sounds like. It's the property of the wire that resists or creates an obstacle for our flowing charges.
Check out the inverse relationship hiding inside that formula. If you rearrange it as I equals V over R, you see that current and resistance are on opposite sides. Imagine a hose pipe. If you squeeze the pipe, thereby increasing the resistance, less water flows out, so you're decreasing the current. It is a perfect inverse relationship. If you double the resistance in a circuit, the current gets cut exactly in half. Simple, logical, and highly testable.
Which brings us nicely to Section 4, Obstacle Course, Resistance.
Why do some wires resist more than others? Well, it boils down to three main factors. First up, the length of the wire, L. A longer wire just means a longer obstacle course for the electrons, so naturally, resistance goes up. Second, the area of cross-section, which is really just a fancy way of saying thickness, A. Think of a thicker wire like a wider, multi-lane highway. Traffic flows way easier, right? So a thicker wire has lower resistance. And third, the nature of the material itself, denoted by the Greek letter rho, which we call resistivity. Copper is just naturally easier to travel through than, say, rubber.
Okay, let's tackle the most notorious exam numerical trick in the whole chapter. I guarantee you're going to see some version of this, the stretching wire trick. The question asks, what happens to the resistance if you stretch a wire to double its length? Your brain might immediately say, well, length doubled, so resistance doubles. Actually, scratch that, it's wrong. You have to think step by step. Step 1, yes, you stretched it to double its length. But step 2, because you stretched it, the wire physically gets thinner. Its area is now cut exactly in half. So, using our formula, the numerator is multiplied by 2 and the denominator is divided by 0.5. 2 divided by 0.5 equals 4. Step 3, the new resistance becomes 4 times the original. Walk yourself through this logic and you will literally never get tripped up again. This obstacle course concept also perfectly explains how we use resistance to our advantage in the real world. Think about it. Why does your electric iron or your toaster use an alloy instead of a pure, highly conductive copper wire? There are 2 high-yield exam reasons for this. 1, alloys have higher resistivity, which creates a lot of resistance, which in turn generates the heat you actually need to toast your bread. And 2, they do not burn or oxidize at high temperatures. If you used pure iron, it might literally catch fire. Alloys just survive the heat. Moving to Section 5, Series versus Parallel. Here is the ultimate shortcut for our final conceptual hurdle. How do we arrange these obstacles? You just have to know what stays constant. In a series connection, the resistors are connected end-to-end, like a single chain. Because there's only one single path, the current remains the same everywhere. But in a parallel connection, the wire splits into multiple branched paths. Because they all connect back to the same main start and end points, the voltage remains the same across all branches. Just memorize this. Series equals same current. Parallel equals same voltage. And finally, Section 6, your ultimate exam cheat sheet. Take a mental screenshot of these formulas right now. These are the 3 pillars of Chapter 11. Current is I. It's Q over T, measured in amperes. Potential difference is the push, V. It's W over Q, measured in volts. And resistance is the obstacle, R. It's V over I, derived right from Ohm's law, and it's measured in ohms. If you have these 3 locked in, you have the tools to solve 90% of the numericals in this chapter. As we wrap up this explainer, I want to leave you with a real-world physics question to test your new knowledge. We know stretching a wire makes it 4 times more resistant, but think about Ohm's law and that tricky condition we highlighted earlier, temperature. If the wiring inside your own house walls gets dangerously hot during a scorching summer day, what actually happens to its resistance? And consequently, how does that affect the flow of current to your TV or your AC? Think about it. Thank you so much for joining me today. Keep practicing those numericals, and I'll catch you in the next explainer.